Hey everyone, and welcome to today's Explainer. I am absolutely pumped to guide you through this one because we're looking at a concept that literally revolutionized modern engineering. We're going on a super fascinating journey to discover exactly how machines learn to automatically correct their own mistakes. I know it sounds a bit like science fiction, right? But it's actually the very real nuts and bolts foundation of our modern world. Let's get right into it.
So, I want you to just think about this for a second. When you turn a dial, push a lever, or punch a command into a machine, how does that machine actually know it finished the job? Hooking a motor up to a power source is one thing, but guaranteeing that the motor stops exactly where you want it to? Man, that is an entirely different beast. This is the fundamental problem of automation, and it's exactly what we're going to solve today.
Okay, let's dive into this with Section 1, the open loop problem.
In a basic open-loop control system, let's say one driving a massive, heavy radar scanner, everything basically just moves in a one-way street. You start with an input demand, like physically turning a dial, which sets the direction for a power amplifier. That amplifier then drives a motor to turn the radar scanner. Sounds simple enough, right? But here's the massive blind spot. There is absolutely zero information coming back to tell the system what that scanner is actually doing out there in reality.
And that brings us to this fantastic quote from our source material that just perfectly nails the flaw here. In an open-loop system, quote, "We hope that the load is doing what we are telling it to do." It's literally the engineering equivalent of throwing a dart while totally blindfolded. You set the dial, you send the juice, and you just kind of cross your fingers that the machine actually listened to you.
And as you can probably guess, hope is a pretty terrible engineering strategy. Out in the real world, unpredictable variables completely wreck your accuracy. A stiff breeze might push against that radar scanner, making it way harder to turn. Or maybe the amplifier's characteristics shift as it heats up, or the motor circuit fluctuates. Because there's no way to monitor those variables, open-loop systems end up being wildly inaccurate. They're practically useless for any really serious heavy-duty applications.
So, how do we fix it? That brings us to Section 2, closing the loop. Believe it or not, the earliest way engineers figured out how to close that loop was just to use a human being. If a person stands there, watches the radar scanner, and manually adjusts the input dial to correct for any drifting, well, the system isn't open loop anymore, is it? The human is acting as an error detector. But while we humans can certainly get the job done, we're pretty slow and we get tired quickly. A vastly superior method is replacing that poor, exhausted operator with an automatic system. An automatic control system is incredibly quick, way more accurate, totally tireless, and it saves a ton of vital manpower.
Which leads us nicely into Section 3, automatic feedback in action.
To pull this off, engineers had to change the fundamental geometry of the entire system. We still have our basic ingredients, the input demand, the amplifier, and the motor. But here is the real game changer. The output shaft angle, which is called theta sub zero, is physically routed right back to the start through a feedback element. We've created a literal closed loop. For the very first time, the machine can actually see what it's doing.
Let's break down exactly how this operates in a continuous four-step cycle. First off, you have the feedback of information concerning the actual real-time behavior of the load. Second, that reality is compared directly with the behavior demanded by the input. Third, based on that comparison, the system generates an error signal which is strictly proportional to the difference between what we want and what's actually happening. And finally, step 4, the servo motor moves the load in whatever direction is needed to reduce that exact error signal all the way down to 0.
Now, the absolute crucial brain making this whole operation possible is a component called the error detector. Just like the definition says, it takes in two distinct inputs, the demand and the reality. It literally subtracts reality from demand. If they don't match up perfectly, the error detector calculates the precise difference and shoots out a signal.
And we call that the error signal. Honestly, I kind of like to think of the error signal as the frantic hero of our story here. It becomes the sole driving force of the motor. It triggers the amplifier, which in turn spins the motor. And here is where it gets beautiful. As the motor turns the load closer and closer to where it's supposed to be, the error shrinks. The error signal is constantly fighting to destroy itself, trying to reach absolute zero. When the output finally perfectly matches the demand, the error signal hits 0, the motor cuts out, and the machine stops right on a dime. Boom, alignment achieved.
So how do we actually build this in the real world? Well, in a practical electrical setup, rather than just abstract blocks, engineers use an AC servo motor and special control transformers. When you turn the input demand, it creates a magnetic field. That field then induces a voltage in a second transformer. And guess what? That resulting voltage is our error signal. It gets amplified and it drives the motor until the physical components align perfectly at right angles. Once they align, the voltage instantly drops to zero and the motor stops. It's this incredibly elegant dance of electricity and magnetism.
Moving right along to section 4, defining the servo mechanism.
Now, just a heads up, not every automatic system gets to call itself a true servo mechanism. To earn that heavyweight title, a system has to meet 4 incredibly strict requirements. Number 1 is error actuation. The whole system must be driven by that error signal we just talked about, not the raw input. Number 2 is power amplification. You need serious torque amplification to drive heavy, industrial loads. Number 3, obviously, it must feature closed-loop control. And number 4, it requires continuous operation.
Let's zero in on that last point for a second, because continuous operation is really what makes a servo mechanism feel almost alive. Also known as having follow-up properties, this means the system is relentlessly stubborn about correcting itself. Imagine a massive gust of wind physically shoves our radar scanner out of position. The system doesn't just shrug and give up. That physical disturbance immediately creates a mismatch between the input and the output. A new error signal is generated instantly, the amplifier fires up, the motor kicks in, and it physically fights back against the wind to return the scanner exactly to where it belongs. It is always watching and it is always correcting.
So what does this all mean for us? The big takeaway from today's explainer is that our entire modern world runs on these invisible loops of feedback. Everything from the cruise control in your car to the massive robotic arms manufacturing our electronics, they all rely on this incredible evolutionary leap from blind hope to continuous, error-destroying action. So I want you to take a look around you today. Now that you know exactly how they work, what invisible servo mechanisms are silently guiding your daily life? And maybe more importantly, what would actually happen if they suddenly stopped correcting us? Thank you so much for joining me today, and as always, keep exploring.